Let's talk data stack and infrastructure. On the previous videos we went through MLOps end-to-end, but before we move forward into details on how to do proper model deployment or real-time monitoring, we'll take a detour into the world of infrastructure and automation. This will give us a platform to deploy our models on-premise, a solution that is not only helpful as a learning experience, but also to support your professional activity as a data expert working remotely. And while deploying a data stack to your home lab can be useful on its own, I'll also fill the gap with knowledge that will help you understand how you would go about porting this to a cloud platform like AWS, GCP or Azure. Today we'll delve into the architecture diagram, the logic behind the design decisions, and the parallels between a home lab and cloud platform deployment. Ready for some solutions engineering? Let's go! So what we've got here is a 4-layer architecture: foundation, platform, services and applications. Let's begin by looking at the foundation layer. This is the layer that contains all major requirements for our platform to be deployed onto. So we do this deployment based on Proxmox. So we have a machine. You can get, a laptop you've got laying around or something like that, and just install Proxmox on it. It's essentially a Debian based distro. It will provide a way for you to remotely provision a bunch of VMs and containers. These containers are Linux containers, so I like C, and the VMs, for the VMs I'm going to use QEMU. And so this foundation layer is just Proxmox and an LXC running with MinIO. Can be really any S3 compatible object store. We're going to need this for several reasons. One of them is that we want to be able to sync our Terraform state, and this will enable us to work on the infrastructure from any machine that can connect to Proxmox. This means that if you are working on your laptop and you suddenly need to deploy something to Docker and the Docker VM does not have enough memory allocated or something, one of the resources, you can increase that very easily just by editing your Terraform file, increasing the memory, Terraform apply, and this state will be kept in a central manner. It can also be used to run from CI/CD on your GitLab. So it's very useful to have this foundation layer with a single object store. Think of this as a cloud platform. On AWS you already have S3 available. This is similar. Then let's look at L2, the platform layer, which is a bunch of QEMU VMs over here. We are going to deploy 4 Docker VMs just to keep contexts separate. From right to left, we are going to have a GitLab runners Docker VM. This will be exclusively assigned to GitLab for CI/CD jobs to run on. We'll have a shared services or core services Docker, where we'll run everything from Postgres to Kafka or DuckLake, and then we'll have the application services, which is a more open Docker host, where you'll be able to spin up microservices or REST APIs or whatever you need for your specific applications. So GitLab over here will be used for 3 main things. It's more than the regular Git repo workflows. We are going to use this for some other stuff, namely configuration management. So we're going to use variables and masked variables, which are akin to secrets, on GitLab, so that we can have our own environment variables. So when we deploy infrastructure to production, for instance using Docker Compose will run from a CI/CD job on GitLab, and it will have access to these configuration variables. If we want to test this locally, we can use a .env and a local Docker host, local Docker deployment. But for GitLab, this is how it will be done. If for some reason you need to customize your own image, for instance, I had to do this for Airflow once, where I needed an image for Airflow that had run a pip install of some dependency I needed available over there. It's nice to be able to track your images and version your own images, so we are going to use GitLab as a container register or a Docker register as well. And this is our platform. Everything will be built on top of this. Next, we've got our services layer. In here we'll run Portainer. This is a non-essential service, but we run it because it will be very easy to connect Portainer to each of these 3 Docker hosts to help us monitor what is happening, if something is down, to be able to access volumes and stuff like that. We'll also run a Postgres instance that will be shared across everything except for a Postgres instance on GitLab, because it's on a different layer. From this layer onward, Postgres will be shared, so it will be used, for instance, by DuckLake for the catalog. DuckLake will also use the min.io instance from layer 1. We just don't use services from higher level layers, so GitLab wouldn't be able to access this Postgres instance because it hasn't been deployed yet. Deploying layer 3 will depend on layer 2, and deploying layer 2 will depend on deploying layer 1, right? So our DuckLake for compute will be kind of like edge computing, so it will use laptops laying around. It might be my own computer, my own desktop, or my laptop, or some other person that might want to work on my data and connects via VPN or something. They can use their own nodes for compute. We'll also deploy Kafka, our event logger, and I'll go into more detail next on why we chose Kafka and not something more lightweight like Redis queue or Redis PubSub. We'll also deploy MLflow for model tracking and registry, and we will deploy Ollama with the open web UI. We can use Ollama for our AI workflows programmatically, or just like a regular chatbot like you do with ChatGPT via the UI. And finally, we will have our applications layer, and this is just an example of what can run on this layer. And keep in mind, both of these layers are running exclusively on Docker containers. The services layer will be run here, while the applications layer will be run here. And so as an example, I've got Fast API over here and Swagger, which is included with Fast API for documentation. But really anything that we need to deploy, it might even be a web app or something, might be deployed here. We might need a database, and we might spin it up over here. And so this is the overview of the architecture. It's quite simple, but I already had basic deployment done. I was not satisfied at all with it, mostly because of this. I kept trying to work on the infrastructure from different locations, and since I did not have this layer or any S3 tracking, whatsoever. I just wasn't able to work remotely, and sometimes I forgot that I had done the previous deployment on one machine and tried to Terraform apply on another machine, and it just erased my state or messed up my infrastructure. So this is really the best way to do it. I also experimented with Kubernetes, but it's completely overkill for something like this, and it's the overhead of having to configure everything in Kubernetes just to spin up a basic Postgres instance or Kafka instance. It just doesn't make sense, really. So I simplified the architecture, the one you are seeing now, to use Docker instead. Let's see how it goes. This is just theoretical. I haven't tested this yet, but this is the idea. And yeah, that's it. Let's go into some of our decision-making process regarding several DevOps utilities that we considered, and also some of these services. So for our first decision, we were thinking about whether we should use OpenTofu instead of Terraform. And the main reason to use OpenTofu, or the reason why OpenTofu exists, is because Terraform changed its license on August 2023 from an MPL 2.0 to a BSL 1.1. The new BSL license is essentially designed for non-competing. So you cannot really change Terraform and distribute it in a way that will compete with the Terraform itself, with HashiCorp. And so since we are not really doing any of that here, we're just doing a tutorial, we're not distributing Terraform or providing any of those services, we can simply stick to the good old Terraform. Another one that I was thinking about was to whether use Podman or Docker. I ended up not using Podman because Podman has a few extra steps that Docker doesn't require. Podman doesn't run with as a service. So if you want to configure something like Portainer to connect to Podman, you'll need to manually set up the Podman socket so you can integrate it to Portainer. Also, if you are running on Mac or Windows, so not on Linux, you won't be able to run Podman natively, so you'll need to run Podman machine init, which is just an extra step that you don't need to do with Docker, although it does something similar underneath. You don't need to worry about it, essentially. It's already pre-configured for you. I ended up just sticking to Docker as well here. So regarding secrets management, the first option was to just use a .env file, and we would just commit a .env.example into the repo, and this file would contain like, let's say, min.io user, admin, and min.io pass, and just your plain text password, and that's it. That's what you can do with a .env file. You cannot do anything like using export from bash, or doing stuff like composing with other variables. You cannot even use double quotes, I believe. So it's quite limited, and you would provide the example like this, or with some pre-filled value, and that's it. That's one option. Another option would be to use, and let's go into .tmp, let's create a test directory. Another option would be to use dir.env, and with dir.env you create a .env rc, and in here you can use export, and in fact I believe you need to use exports. And let's say that I would want to use set our go home to home/go, And if I leave here and I print go home, you'll find nothing. But if you just run dir inf allow, then if you echo go home, you'll see this variable is within context. If you leave this directory, it will be unloaded, so it exists no longer. You go back, it will be here. Again, we would need to provide some way to create this initial .envarc, maybe with a .envarc example or something like that, similar to .env. It has the benefit that it gets automatically loaded. And each time you modify this file, let's say I wanted .go instead of go, I'll go into the directory and I'll need to run dir env again, otherwise it will not load anything. And there you go. So this was also not ideal. Another option that we considered was using something like Ansible Vault. We are not using Ansible, so it wouldn't make sense to use Ansible Vault. And Ansible Vault also fully encrypts a secrets file, and it can be committed to your repo afterwards, but it's not easy to track the diffs between these files, so they are always fully replaced. So one thing we considered was to use SOPs, secret operations. This was originally created by Mozilla, and what this does is similar to Ansible Vault, but instead it just encrypts values, not the keys. So you can keep a JSON file or a YAML file. This actually looks quite interesting and I might use it in the future. Another thing we considered was HashiCorp Vault. This seems to be quite beloved by the community and has great integration with Terraform as expected because it's from HashiCorp. There even is a browser extension for this. I don't know if it works as well as Bitwarden or some of those extensions to fill in the credentials, but this might be interesting. But it's yet another service that you are running. It adds to the complexity, and we want to keep this as minimal as possible. So we ended up not going this route. Since we are using GitLab already, we thought, why not simply use GitLab CI/CD variables? And these variables can be defined directly within the GitLab CI file, but they can also be defined in the UI. And this is the way we are thinking about using this. And there are project level variables per repo, group level, you can create those groups, or instance level, which means that it's widely available to your GitLab instance overall. So I think this is an interesting approach, and also you can mask the variables. So if they are visible, they are just regular configuration variables like URI or something like that, without credentials obviously. And if they are masked, they are invisible, and masked and hidden means that no one will have access to these variables once they are first set. They are masked, you can unmask them, I believe, but I think this is the distinction. So I think this is more than enough and keeps our system simple. Another thing that we needed was a container registry or Docker registry, and essentially we could just spin up a registry using this image over here, official by Docker. But of course this is headless, it doesn't have a UI. And one UI, a simple UI we can use is Docker Registry UI. This is available as a simple Docker image, and it just provides an interface with very basic features on top of your Docker Registry container. I actually ran this before and it works great, but we are running GitLab, right? So since we are running GitLab and it provides a container registry, why not keep it simple again and just do everything within GitLab? Since we'll do deployment via GitLab using CI/CD anyway, it's great that our images will already be available within GitLab itself. So this is really a win-win, and it's self-hosted, so it's within your own home lab. This doesn't mean you cannot use a public repo for your code and then integrate into your home lab, and I'll show you how to handle this in a later video. And another thing that we considered while doing research for this was to use Harbor, but Harbor is a bit overkill because it's mostly to run on Kubernetes, there is a demo that is running online, so let's quickly check it out. And so this is what Harbor would look like. It's a really nice UI, but it's got a ton of features that we don't really need, you know, multiple registries, and then, you know, replication. We don't need any of this. We are not going to deploy Kubernetes as well, so this would need Kubernetes to run, and so we didn't go this route. We ended up just taking advantage of GitLab's container registry for this. So next, regarding configuration management, so we'll need to install stuff like GitLab, and we can't use it out of the box. We'll need to configure stuff like Docker GitLab runners and other stuff we might need. And so we need to have some way to manage those configurations. One way is to use Ansible. What we see here is Ansible Galaxy, which is just a library of Ansible collections and roles that you can reuse to install stuff like GitLab or whatever. So GitLab web interface, for instance, you've got this role over here. There is usually some documentation. Let's try this one. Yeah, and as you can see, there is GitLab server. It will tell you how to configure GitLab server over here. And there is GitLab runner, which is required for your CI/CD usually, or at least in my case, I'm going to use Docker for this. And there is GitLab common as well. So you could use this, but I've got kind of a love-hate relationship with Ansible. I think it can get overly complex at times. So I thought I would try something different this time. So I'm going to use Packer instead. And Packer is again from HashiCorp. It can be defined using the same HCL language that you use with Terraform. And essentially you just set up a base image. You do your configurations with a script usually. You store those, you create the image once, then you can use it as many times as you want. The image is pre-configured, pre-set up. And the advantage of Packer is that you can use Packer to produce QCOW2 images, which are the ones that run on Proxmox using QEMU. But you can also use Packer to produce images for cloud platforms, so or even Docker images if you like. Instead of using a Docker file, you can use Packer. So it's very nice to have Packer as a skill. And it's also nice to have Packer in your project because it makes it easier. If you'd like to port this into a cloud platform, you already have Packer. You just need to produce an image for a different platform that is not Proxmox. There is not a Proxmox VM, a QEMU VM. And so I'm going to use or try to use Packer to deploy and configure GitLab. Let's see how it goes. So very quickly, let's go through our core services. First, we're going to use Portainer to monitor and manage or to test stuff on Docker, on our Docker instances. So we'll have 3 Docker environments over here. As you can see, it also supports Kubernetes or Podman after you configure the socket. So we are going to be running this. We're going to be running Postgres. It is very nice relational database for general purpose, but it's also supported by DuckLake for its catalog. And since we are going to run DuckLake, and running DuckLake really means that we need a catalog and we need storage. For catalog we are going to use Postgres, as I said, and for storage we are going to use MinIO, which is an S3 compatible store. Then we are going to use Kafka. So on a few notes on Kafka. Why Kafka? Why not Redis Q or PubSub or even a custom gRPC microservice architecture? So having middleware for inter-process communication is usually easier to handle than building your own custom gRPC solutions. That would only make sense if you needed really high performance. So we're not going to do that. We are going to use some kind of middleware. So it would be between Kafka or Redis or something similar like ZeroMQ or a lightweight solution like that. But we are going to use Kafka mostly for the learning experience, first of all, because this is a lab. But we know that Kafka can be the single most useful piece of software you could use in production systems, and this is not production, but so it's very nice to learn how to use it because it can help your app scale. So for instance, you've got a broker on Kafka where you have multiple topics. If you're having high traffic coming into your application, as long as it goes through a topic on Kafka, you can scale horizontally and create several partitions for the same topic within a group. And so this is a way to scale up and down very easily. And also it helps you stay compliant because it will keep logs of every event that goes through. Of course, you need the space to keep all that. You need double the space, and as you know, storage is cheap, and this will make it easy for you to, if you are, trying to get certification or something like that, trying to get your company certified, you will be able to show that you are able to track your data pipelines from its origin to the end. And it also helps you, this replayability that Kafka offers also helps you in case you need to debug your system. So you'll be able to replay a given topic from a given date, and so you'll be able to feed it to your development system and try again. So this is also helpful in that way. And the base deployment just requires about 600 megabytes of RAM, which is not that much, although it doesn't provide much as well. It doesn't provide, any kind of high availability features. There are not multiple instances running. It's not scaled up. It just provides basic replayability and, peace of mind knowing that you are fully integrated with Kafka, and if you need to scale it up, you will be able to do it very easily. Another thing that is very common in stream processing, so you are feeding data into Kafka and that data will go someplace. Usually you create mini batches of data or even larger batches of data to process, and you want to process that as a stream. So you can either implement that yourself and have a buffer in memory in Python or something and keep consuming the messages sent to that topic, or you can have something like Apache Flink running that will help you with stream processing. But this is in Java, and there is something called FOST, which is a Python library that does a lot of the same things that Apache Flink also does, but keeps you in Python. So if I ever need to implement a more complex workflow to consume or to process a stream coming from Kafka, I'm thinking about using FOST instead. So I'll not deploy an extra service for that. And then we've got MLflow, which is, for model tracking, and acts as a registry as well. We've talked about it before, so you can go check our MLOps end-to-end video if you'd like to know more about it. And I'll also like to deploy an Ollama instance with the Open Web UI, which kind of provides your own ChatGPT in-house. It will be either much slower than the original ChatGPT or provide worse answers than ChatGPT, just unless you, of course, you have a massive infrastructure where you can run this, which I doubt it. You won't get high quality LLMs using consumer hardware easily, but it can be used for some experiments locally either way. And you can install, even the GPT model is now open source, has been recently. You can install any of these well-known models. There are several versions, but keep in mind that you'll need to, since we are running on Proxmox, we'll need to install NVIDIA drivers on the host machine. This means on the Proxmox operating system, and then we'll need to install those drivers on the VM, on the Docker VM, and we'll need to pass through and all that. I'm not sure how to do that yet, but I believe this will be a bit of a challenge. And then we'll need to also make that available within Docker, which I believe will be transparently done. The Docker Compose configuration should be enough, but yeah, we'll see. This might be a bit of a challenge, this one here. And finally, let's talk a bit about how you would transfer this knowledge that you'll gain to a regular cloud platform like AWS, GCP, or Azure. So for the foundation layer, we essentially just need something like Proxmox that provides VMs and containers, and we need some object store. So if you go to GCP, Google Cloud, you'll find this compute engine, and this provides virtual machines. So it's just extremely similar to creating your own Proxmox VM. Since we are going to use Terraform, there are, if you search Terraform registry, you'll find a provider for GCP, and you'll be able to deploy or to provision a virtual machine on GCP as easily as you do on Proxmox. So if you can really learn a lot about cloud by just installing Proxmox and doing your own virtualization using Terraform and the BFG Proxmox provider. We'll talk about that on the next video. If you want to use AWS, you've got Elastic Cloud Computing, which is EC2, Elastic Compute Cloud, and these are also virtual machines. That's just it. There's no secret sauce here. There are multiple instances with different labels, and cloud engineers usually get to know them very closely. They know which ones to specifically choose to minimize cost for the company's specific needs. So that's really just a familiarity with after working on this, but other than that, it's just a virtual machine. You've got this as well on Azure. It's called Azure Virtual Machines. It's quite clear. There is no weird naming as is done here. And then regarding object storage, you've got on Google Cloud, you've got cloud storage, which is it's not an S3 compatible API, but it is widely supported as well. Then you've got the classic S3, which stands for Simple Storage Service. And finally, you've got Azure Blob Storage, which is their own option for object storage as well. And these are all widely supported. For instance, if we go into DuckLake and we go into the DuckDB extension and search for choosing storage, As you can see, AWS S3, Google Cloud Storage, and Azure Blob Store are all supported. So, and this is very commonly available elsewhere as well. So, and this is just a quick example of how you can map what we are doing on our home lab with Proxmox and the VMs and everything that we're going to install. How you can do that on using regular cloud platforms. Then regarding platform, we'll want to run Docker and we'll want to have a Git repo, right? So for Docker, we've got Fargate, and this will let you deploy your Docker images. This is an option on AWS. For GCP, you've got Cloud Run, so you can also host your own Docker images. You just need to know the names of the services. Sometimes there are multiple options for the same thing. They scale differently or have a different approach to availability of your Docker images. Some of them, if they are idle for a while, will be scaled down automatically or even turned off to 0. We've also got Azure Container Instances, which is similar but by Azure. So this would replace our Docker VMs. You can even get Git on AWS directly using AWS Code Commit. This usually integrates with several DevOps tools as well. There is GCP Cloud Source Repositories for GCP, Azure repos for Azure. And the same happens for the services that we are deploying here. For instance, for Postgres, you've got Amazon RDS or Amazon Aurora. For GCP, you've got Cloud SQL or AlloyDB. And for Azure, you've got Azure Database or Cosmos DB. DuckLake doesn't need its own cloud service because it just integrates with Postgres for the catalog or the object stores. For Kafka, you've got Amazon MSK or Confluent Cloud, which is by the official creators of Kafka. And this runs on GCP and Azure. For MLflow, it's similar to DuckLake, so you've got you can run it on a VM or as a Docker service, and then you can integrate it with the backend store. Can be Postgres, and it can use cloud object stores to store the artifacts. And for Ollama, they've got each has their own model. So there is Titan on Amazon Bedrock, there is Gemini on Google Vertex AI. You know, Gemini is also available as a regular chatbot. There is Phi on Azure AI, which is a model by Microsoft that you can find on Ollama's website as well. There is Azure OpenAI service because they have a partnership with OpenAI. They also provide this. So as you can see, everything that we are going to learn in the next videos is quite easily mappable to cloud platforms. You can go into Terraform, search for a provider for that service, and just, you know, fill in the configuration, Terraform apply, boom, you've got a Docker image running on AWS or whatever cloud platform it is. So this was planning, and you got to know that it's not that hard to translate these skills to the likes of AWS, GCP or Azure. Now let's see how it goes when we put this into practice next time on premise using Proxmox. We'll begin by setting up Terraform to access Proxmox, deploying the S3 compatible object store and using it to store the state for a separate Terraform project that will deal with the Docker VMs and the GitLab deployment and everything that is platform level. The next few videos will be on this topic, and I'll keep them on Data Lab Infra playlist, and eventually we'll circle back to MLOps again once we can use the Infra for application level deployments. This should be fun. Until then, don't forget to read this week's blog post on datalabtechtv.com, follow the channel on Blue Sky, and join Discord to discuss all data related topics. Seriously, If you've got any technical questions that need a more up-close live discussion, this could be fun. Don't forget to drop a like if you enjoyed this video or found it useful, and subscribe for all things data.